Hi, everyone. Thank you very much for this invitation. I'm very sorry I cannot give my talk personally. I overbooked this time slot, unfortunately, because I got confused with the time zones. My bad. Nevertheless, I'm very happy to present my contribution to this workshop, and I will talk about neuromorphic systems for assistive robots. In my work, I'm interested to build neuromorphic technology for assistive robots. Assistive robots are supposed to work side by side with humans. And my biggest claim is that these robots cannot be blind during movement. They need to see the environment around them and update their movement on the fly as things change in this environment. We humans take this for granted a lot because in our vision system has two parts. One of them is the slow part where we consciously perceive objects around them, recognize them. And for that part, us watching a movie of 20, 30 frames per second is enough to create this illusion of smooth movement. However, we have another visual part, which we use during motion. And you can think of running down the stairs and closing your eyes. You really feel super uncomfortable when doing that. However, when you run down the stairs with your eyes open, you're not obligatory, observe every feature on those stairs, every edge. No, it's just on the periphery of your vision. Some information gets into your system and makes you move stably, smoothly. You also use it when you control your posture. You also use it when you do some fine manipulation with your hands. Now, the robots today don't have vision like that. The robots rely on today's camera systems, that perceive the frame with 20, 30 milliseconds. Then they send this frame to the computer. There you have your algorithm detecting objects, detecting there and segmenting them, taking another 100 to 200 milliseconds to process it. And then it takes even longer to plan your movements. So if you observe robots working, if they use vision, they get very, very slow if they use visual surveying. Between the moments when they don't use vision, when they're blind, they are fast, they're amazing. But the moment the vision gets integrated, they slow down. So we are really lucky that we have our event-based vision sensors that got rid of the concept of a frame, so they don't wait for the whole frame to be collected and sent to the computer, but every pixel is allowed to detect luminance change events and send them asynchronously for processing. This allows the sensor to be much, much faster than regular camera and really approach this real-time visual processing that we envision, that we dream of. Now, the events by themselves are relatively silly, right? The event by itself doesn't tell me, shall I go in that direction? Is it an obstacle? Is it a target? Where is it exactly relative to myself? So we still need to compute with those events. So in our work, we combine event-based camera, event-based sensor with a matching computing hardware and run algorithms on this computing hardware to make this camera useful for robots. What are the example of algorithms? The one that detect the identity of an object, recognize an object, the ones that detect the position of this object relative to the robot or its velocity, for instance. And then this allows us to enable all these applications of robotic technology in human-centered domains where the robots need to move safely in dynamic environments. So our dream is to connect a neuromorphic sensor directly to a neuromorphic chip. Now, neuromorphic chips, they have a very similar computing framework that matches the event-based information representation. On a neuromorphic chip, you typically have this asynchronous parallel system of computing units, the cores, that can take in the events one by one as they come in, and then feed the spiky neuronal network with these events that do event-driven computation, that is asynchronous, local. So if your event stream is sparse, only neurons that get events will make computations. So you have a very power-efficient system. However, today we cannot connect event-based sensors directly to neuromorphic chips. And one of the reasons why it is difficult to do that is lacking standards. Lacking standards in defining how do we connect the events, this X, Y coordinate, polarity, and your temporal timestamp. How do we map now these to our neuronal architecture? How do we assign each event to a neuron? What format shall we use? If we would agree on some standard there, I think that would make development of the hardware and software interfaces between different event-based sensors and different neuromorphic computing platforms much easier. So today we don't really have this standard. There are some heroic efforts to connect individual sensors with individual computers, but in general, this is not possible. So what we have to do instead is to connect our event-based camera to a conventional computer, and then connect the computer to the neuromorphic chip. When doing that, it doesn't make sense anymore to send individual events, to the computer over USB connection, and then send, these events, pack them in some variables, and then send them to the chip. So here we really have to aggregate events in little chunks or batches. In this particular example, we additionally combined our event-based sensor with a conventional camera, RGBD, the depth sensor, to create the overall application. So in general, when we have our event-based camera, the first question that we need to ask is, where will this event go in terms of computing hardware? Now, our final goal is to connect event-based camera directly to a neuromorphic chip. And not quite there yet. So today we do use a computer on the way. So we connect the event-based camera to a computer, and then that goes to a neuromorphic chip. Or we might want to connect our event-based camera to some other accelerator, or maybe to a microcontroller, or maybe to an FPGA. So these are all different hardware options. The next question we have to ask ourselves now when thinking about the standards that we want to develop is, what do we do with these events? So what kind of event-based vision algorithms do we envision to use with the camera? So the first kind of type of algorithms that we would like to use is we would like to align our event-based sensor with some other sensors. This could be an inertia measurement unit. This could be another event-based camera if you want to do stereo vision. This could be a conventional RGB and then depth camera with different frame rates. And this alignment can mean two things. One is the spatial alignment. If we have two cameras, we want to know each pixel in one camera to which pixel in another camera it corresponds. So that then we can combine these two streams of data in one assessment of what is out there in the world. And another type of alignment is a temporal alignment. So we need to synchronize our sensors temporally. Now, our event stream has very high temporal resolution with 10 microseconds potentially. And then we have this slower RGB camera, but these two frames need to be aligned. So this is the first question we need to keep in mind. How do we transmit this information in our data format that helps us to align the sensors? And then, as a second step, we do all our algorithms. And the algorithms could be some deep, possibly spiking neuronal network. So it can be asynchronous or synchronous, depending on whether we have neuromorphic hardware at hand or not. It could be some not deep neural network-based architecture that could be sparse, meaning that this algorithm could make use of each event and can do event-by-event computing. Some examples are depth from motion, or optical flow computation, where you look for correlations in small spatiotemporal neighborhoods of each event. And this computation kind of profits from event-by-event character of event streams. We could have some other algorithms, for instance, dynamic neural fields. So we take all architectures, which are neuronal architectures that have layered structure that receive input from event-based camera in a one-by-one fashion. And these architectures could both use event-by-event stream and then do kind of temporal averaging within the network. Or they could also receive little frames and aggregations of events. So as you see, kind of the big question around which I'm already circling all the time is, shall we use events or shall we use event frames? And I don't have a very strong opinion on this topic, so I think both can be useful and needed. The first, as already mentioned, we are basically forced to use frames if we connect our sensor not directly to some asynchronous neuromorphic processor, but go over a PC. If we have a USB cable and then another cable, we really don't want to make communication in an event-by-event fashion. With a couple mega events per second, we will just spend a lot of time and energy doing the communication that way. Sending events in batches or in frames makes sense then. On the other hand side, this concept of event frame is useful, for instance, for calibration. So if I need to align my event-based sensor to a non-event-based sensor, it's good to get rid of the temporal kind of component and just have spatial frames for which I can now do this geometric computation to compute the transformation between the two frames. And then I can use conventional OpenCV tools, my checkerboard, do the calibration. Now, it is important which frames do I use. So there are two types of frames, as you probably know. So one is time-based. So I just collect all events that arrive in some time interval, 10 milliseconds, let's say. If I do that, I'm really very close to conventional camera then. And then I should ask myself, do I really want to use an expensive event-based sensor, or can I just use a regular camera instead? There's another type of frames that makes kind of more sense is when we collect a certain number of events in a frame, for instance, 1,000 events. Then the temporal extent of my frame will be variable, will depend on how dynamic the scene is. If my camera is moving through the scene very quickly and I receive a lot of events, then my frames become very thin, so I effectively have very high frame rate. And if there's not much happening, my frame becomes kind of broad in time. And then I don't spend kind of time and energy sending all the redundant frames. Now, if I have my pipeline, event-based sensor, computer, neuromorphic chip, it is important that when I send those frames, especially the event frames with a fixed number of events, that they don't send the whole matrix over, because this matrix will have a lot of zeros, for the whole camera resolution, and will have a fixed number of non-zero values, those 1,000 non-zero values. So it has a fixed sparsity. So I believe in our algorithms and in our formats and data representations, it is important to make use of this constant sparsity, which I have set with my own hands in advance, if I use event frames with fixed number of events. And there can be some algorithms that really require event-by-event processing, just for the sake of this algorithm working, or for efficiency. I have a couple examples for you. So for instance, we've once built an obstacle avoidance system for a drone inspired by an insect, so locust giant motion detector neuron. This neuron has kind of branches that go to the visual field of this animal, or in our case, to event-based camera. And events from the event-based camera, they go on a layer of neurons, which then aggregate these events and let them go through a network that detects moving stimulus. So the stimulus that expands in the visual field and ignores everything else. And this architecture can work in this asynchronous mode. So events arrive to the neurons. The neurons do temporal aggregation. They don't need the frames. They make the frames themselves with the temporal filtering of neurons, which I have control of, which can be even adaptive. So I have a lot of power when I can tune these parameters in my network directly. And it can work very, very fast. Another example where event-by-event computing is used is in work of Guido de Kroon, where he has implemented this landing controller, controlling the landing speed of a drone based on optical flow divergence. So again, that algorithm, the optical flow calculation, takes into account local neighborhood of each event, local in terms of time and space, and determines local motion vectors. So this computation runs very nicely, especially on neuromorphic computing hardware. If it's done in event-by-event fashion, I don't need the frames. It's actually better if the events just come and are naturally integrated in space and time by the neuronal network. Another example is the tracking architecture that we have published a while ago on Loihi. It's a very simple moving blob detector. Again, so we have connected event-based sensor directly to the neuromorphic chip. That was possible for this particular configuration. And on the chip, we had this simple neuronal architecture with just two layers of neurons. The first layer receives events from the camera, basically in a one-to-one fashion. And the neurons on this chip, they integrate these events in time, with temporal time constants of Lick integrated fire dynamics. And this layer has some lateral connections, like Gaussian, Mexican head connectivity to itself, so that this layer does some filtering. It gets rid of individual noise events and forms blobs where events are coherent in time and in space. So it's some moving blob in the environment. And this layer can track multiple objects that move in front of the camera. The second layer has stronger inhibition in this layer, so it inhibits most of the objects and only leaves one and tracks one object. So again, in this network, all the aggregation and frames is done by the neurons themselves. Similar example is with the half transform. So we also do tracking, but now we do tracking in the half space. Half space is a space of parameters of the lines. So here, each event in the visual field votes for a certain line, for certain parameters of the line. So each event generates a line kind of input in a layer of neurons, and then the intersection of these lines kind of gives the aggregation of votes for a particular line. So if we have a line moving in front of the visual field, we'll get this estimation of the line's parameters in the network. And when this estimation is done, it's defined by parameters of my network, by the threshold of the neurons that can be adaptive, that I can learn, that I can set, when designing my architecture. And the network works in event-by-event fashion. Similarly, for 3D perception, if we do depth from motion, we can use elementary motion detector. This is again a neuronal network where the neuron becomes an event and then kind of correlates this event with the previously perceived events in the neighborhood. And then makes a decision about the optic flow, the movement, and integrates the self-motion estimation and makes estimation of the depth from which this event probably has arrived. Again, event-by-event processing, particularly efficient on neuromorphic chip. Another example for 3D perception with structured light. So this is when we shine light in a controlled way in the environment, and then we perceive it with the event-based camera and can triangulate where this point was in 3D. Again, it works nicely in an event-by-event fashion when my network can decide, okay, was it the laser pointer light or was it just some distractor moving around? No need to have frames there. Another example where we actually do need frames because we want to do object recognition here. We want to learn objects and to recognize them. And object recognition typically relies on the spatial distribution of features, spatial pattern. So actually, we don't, strictly speaking, need the temporal component. So we can aggregate, which we also do here. But because our scene is a priori static, we create these frames by moving the camera a little bit. We call it a microsaccadic eye movement. So we have this controlled movement. In this movement, we collect the events and create the frame. Now, the parameters of this movement could be sent together with this frame and could be used for object detection. If I make horizontal movement, I look for other edges or features than if I do vertical movement or if I do circular movement. So something to maybe also take into account when thinking about standards and formats. Now, this is how these little event frames look like, the collections of events during the microsaccade. And then we do object learning in more or less conventional convolutional neuronal network. Now, of course, many people do use these convolutional neuronal networks in their pipelines. And they are, especially if the input comes over the PC, it does make sense to work with frames. But the width of these frames is very important because the one that you have used by training, you better stick to it during inference because your neural network will learn kind of the depth of your frames as well. So I think there's still something to be understood and appreciated more strongly in the community, how to deal with these event frames. Computation. Okay, I will conclude very quickly. The first, event-based sensor is a path towards real-time vision that we need to enable assistive robotics, make it safe. I've named you a couple examples of event-based vision algorithms: depth perception, object detection and recognition, and object tracking. Some examples. Today, image-based frameworks and tools really prevail. You have OpenCV tools, and then you have all the deep learning tools, TensorFlow, and so on. They all use this concept of matrices, of images, of vectors. And so when we have to decide, do we use event-by-event algorithms, or do we use these event-frame algorithms, they attract us very strongly on the side of image-based frameworks because their tools are so nicely developed. So, but my hope is that tomorrow we will also have an event-based computing framework as strongly developed as the conventional image-based one. And this requires new concepts of data transmission and storage, and that's certainly a subject of longer discussion. Shall we have some message-based computing? Shall we send vectors, between devices and populations, neuronal populations? Shall we use sparse representation because we know the sparsity of our vectors? Shall we keep the meta information about these events, like for synchronization, for calibration, or like about the movement that has generated this event frame? Or shall we use very lean representation of just spikes like the brain does? And overall the question, how brain inspired do we want our computation to be? Thank you very much.